course, way. This is not exactly how servers work. In particular, I'm going to talk about getting the DS record. Normally, I would have that on the way down, but I'm going to pretend I don't get that. So this time around, this is the scorecard I'm going to be using. This shows on the left-hand side, those are the same nine boxes that I had before. And I have key numbers in there to help differentiate this as I go through there, a little more detail. And on the right-hand side, I have how the bottom one is related to the one above it. How do I build the chain? For example, at the bottom, www.example.com, A record 192.022, signed by K42694, which is the key above it. And that goes all the way to the top. And the top one, of course, is what I call my trust anchor. So this is what I'm going to be building as I go through the next set of slides. So let's start with the dig. I use dig here as an example of querying the DNS, the domain unit groper. I ask it for www.example.com's A record. I get back my A record on top, and below that I get a signature record which has information in it. I'll talk about that in the next slide. And that's where I start my work from. So, and actually to go into that, right away. A couple of things that are inside this key. If you look at this record here, I blew this up and put a different font, but it's the same record. I have the owner name, www.example.com, and I have to think RRSIG A. RRSIG here is, if you're familiar with the DNS at all, that's normally where you put the type of record it is. And this is a resource record set signature. That's what this is going to be. The next part is there's a space, and there's another type here, which is A record. And A is something you might be familiar with because that's the address record. That's the type the signature covers, meaning that it belongs, and I'll go back a slide. This A record here, this A corresponds to that A right there. Now I have some numbers here I'm not going to explain, but I have these two long numbers, and these are dates. Curiously, for some reason, we put the end time first, and the second number is when we start. This is the time span in which this signature can be considered to be valid. The reason for the signature time span is so that no one can replay this. If I sign some data from 3 years ago and then I change my servers around, no one can use those signatures to mess with your mind today. We don't want people to replay old signatures. So we have from this time here in the orange box until the red box to use this signature. And I will refer to this throughout the slides that the time is important, only to remind people that time is important here, but though it's not a major part of the theory. And finally down here I have, in this purple box, the key that's used. The key here is identified by two numbers, or two things rather. The name, which is the owner of the key, and then also this thing called a key ID or key tag. I've actually forgotten which we call it over the years. It's just a number which helps us find what of many keys might be used for this signature. So let me step back 2 slides again. I did this dig. I break it down this way. And what I end up here with my scorecard right now is I have www.example.com, and this is my information, and I have an unverified signature. I have a signature, but it doesn't mean anything yet. So what I need to do here is I need to solve that yellow box. I need to find out how do I verify the signature. Well, I have data, which I talked about earlier. I have a digital signature, and I need to get a key, but I don't have it. In order to compare this to find out whether it's good or it's a bad piece of information. So being a DNS, I look it up. I look up the key. I said, now give me the key, and this is, again, the bottom of the stack of servers, and I get back an answer saying that example.com has actually 2 keys. It has the key I want, 42694 up here, and another key, and they're signed by one signature. It covers all of this. DNS works in sets of data, not single things. So I'm sending back 2 keys and signed by one of them. And the date of this is from February 3rd to April 1st. I'm okay because I'm doing this in February. So so I get more than one key back. One key is a KSK, one key is a ZSK. And I say 257 and 256 are important. If I notice here there's a 256, that means it to me, someone who knows the numbers, that means this is a ZSK. It's a plain key for signing data. This 257 means, which if you know how flags work, it's one other flag bit is set, says that this is going to be a special meaning, it's a KSK, it will do key signing key. So that's why I have multiple keys and one signature. So when I have that response come in, I now have example.com key and the 2 keys on the left-hand side, and I have 3 unverified signature boxes. I haven't done any of my crypto checks yet. But now I do my check. This is the check from a few slides ago, and I say, okay, I have the data, I have the signature, I have the key, which I now look at, and it validates. Trust me, it validated. I'm not going to show you that part here. So now I have progress. So the bottom part is turned green, it's signed. So the next thing, though, is as I go back here, I've got these two unverified signatures. So let me try to take the 42694 signature, run it through the same process, which I already have. Again, the previous message I showed, this is the same replay of what I showed before. And I check that, and it works. So now I have it signed by there. But I have this other key. Let me, just for good measure, I'll try to verify that the data, the signature, and the key, it checks. And I have this thing here. But I made the self-signed signature not green, it's yellow, because a self-signed signature really isn't very important. Now, I said initially that I'm going to trust the key at the top of this. There's the top of the scorecard, I had a trusted key. That's what I believe in. I don't believe anything else but that one key in the way I'm set up. So how do I get up there? This is where the DS record comes in. The DS record is going to help the layer above point to that key and say, yes, that's the key that you should see there. You should see a self-signed key at that point. So I'm going to do this check here where I have the key, KSK, and I need the example.com's DS record, which has a hash value in the middle of it. But I don't have that record. Well, I probably would have, but let's say I don't have it. So I have to go get it. So I dig for the example.com DS record, and I get back an answer which has this DS record and has a hash. And it's also signed. That hash is going to have to do be cryptographically related to the, actually just a hash relation to that key I have. So I will go through this, and I note that everything else here is okay, that the signature dates are okay from February until March. And I check the hash, and I get an okay. And so what I have now is I have this turn green, this hashes to example.com DS, so I'm getting somewhere. But I now have this unverified signature to deal with. So I want to check this. I have the DS record, I have its signature, but I don't have the key from COM to get that. So I asked the COM server, I asked COM, or asked the DNS for the COM's keys, and I get back two keys again, 256, 257, that's a ZSK, KSK signature from February 6th to March 21st. It all checks out with time. So now I do the example. I check the DS record is validated. The signature works. The cryptography works. And I wind up with this DS record is signed by this key. And these two keys up here have unverified signatures, and I have to repeat. I'm basically going to start repeating myself. But fortunately, I'm 2/3 of the way up. So here I have the keys for COM. I get the signature signed. There's a signature along that. I check it. I have that. This gives me the ZSK of COM is now signed by its top key. The top key, it's signed by itself. And I have now self-signed signature. So again, now the COM and everything else is okay, but I didn't trust this key out of the box. I don't trust that key right away, so I need to find proof that it's the right key to go to. So I go through the check here, the DS record, where I have the key, I have the DS record, and I see that I go off and get the DS record. I come back with this COM DS record with a hash up here, and it's signed. The dates are okay. So now I see it's signed by a root key up here. I'll keep these notes. I check the KSK up here. I check the DS record, and it works. Turns out that all the math works. And so now I have the hashes of the hashes to com.ds from this key. But I have an unverified signature of the DS record, so I need to check that. I don't have the key I need down here from the root, so I ask for the root's keys. And I get back two keys, 256 and 257 come back. And the signature, and again, the dates check out. And when I go to check, I see that the root key, the DS record is going to verify from that ZSK the root zone. And so now I'm up to here, where I have this DS record is signed by the root zone key. I have its unverified signature, and I have an unverified signature. This is actually the same signature over these two keys up here. But now I actually see these keys. Now, I want to check to make sure that the ZSK of the root zone is fine, so I go through the same cryptographic check. I have all the data I need, and I check it, and it works out right. So now my scorecard shows that this is signed. The green box is signed by the top key, and I have an unverified signature. At this point, it gets kind of weird how it happens, because here, I say I trust this KSK 20326. I have that configured in my server. But I also notice that I get a copy of that over the network, and I have a signature that comes from it. So if I verify that signature with a key I received over the network, I have to be careful that I'm trusting the right thing, because someone may have changed the key. But I want to make sure I trust what I have in my trust anchor. So I want to make sure I get back to that one trust anchor, and the implementations have to do this correctly. That they check with the key I have configured, not the key I just learned. So, I don't want someone lying to me about this is the key. Maybe implementation detail, but I do one more check to make sure the trust anchor is truly identical to it's truly identical to the trust anchor, that key up there, before I rely on it. So after I do this, I come up here with a complete chain, which shows the root key, always trusted. It signs the ZSK of the root zone. Which signs a DS record, which points to this DS record, which signs, this key rather, which signs the ZSK, which signs the DS record for example.com, which points to the key for example.com's KSK to its ZSK and on down to the data I have out there. So this is kind of complicated. It's it's tedious, actually. It's a good thing computers do this stuff. I should point out that what I showed you is probably the worst example of how DNSSEC works, because generally we have caching through the DNS where a lot of this information may already be in cache. Normally, if I have a very busy recursive server out there and I look up www.example.com and it doesn't know the answer, it goes off and will ask. But it may already know where com is, or it may even know where example.com is, and in that case, it's just a simple one or two messages go by there, validated information is already in my cache, and I'm done a lot quicker than this. So, and by the way, I'm actually going through a lot quicker than I thought it would. So, for no answers. Now, so what I showed you an example was, in the DNS, was what we call a positive answer. There's actually data there. And that was easy in DNSSEC to design because we just took the data records that DNS already had and said, well, we'll just sign what we have there. But now we have a problem in DNS is that how do we say the data isn't there? Now, the way the DNS traditionally said data is not there is by sending back to you nothing. It was possible to send out a question and come back with no answer records, no information, and you had to induce that there was just nothing there to work from. So we kind of had to invent the way this would be done. We had to come up with some way to put data into the DNS to say there's no data here. Sounds kind of funny. Now, the approach, there's two approaches. One's called NSEC, one's called NSEC 3. And the approach in NSEC was to say, this is how I'm going to prove to you I don't have what you want. We're going to assume that all the data comes in order. We can alphabetize, whatever alphabetize means, all the names in your zone, start to finish, and all the records inside that will do something special. And the way this is going to work is that when you ask me a question, I want something particular, I'll say to you, well, here's a name before it, a name after it, and here's what's there at these places. And it's kind of like saying, you know, you go home and you ask your parents for like, what do we have for dinner? And they'll say, well, here's the refrigerator, here's what's in it. It's not exactly directly answering the question, but in a way saying that, you know, well, I don't have an answer for you, but look in the refrigerator, there's nothing there. You know, you're not going to have dinner. Basically, the DNS would say, here's what I have, and you see I don't have what you want. Now, it sounds kind of funny to do that, to show more information about you than you otherwise would, to say, no, you don't have the data. But the reason for this was when DNSSEC was designed, we didn't have the ability, we didn't trust the servers on the network to hold information to create cryptographic keys. Servers back in the 1990s, when this stuff was, the problem statement was put together, at that time, host security was so poor, no one would ever think of putting anything secure on a server facing the internet. Even today, it's kind of risky to do that, but it's a little better than it used to be. So we tried to make sure we always had the answers before we even started the server. Now, nowadays, there are people saying, well, we have better security, we can do online signing, do things different ways. Some people advertise that. The problem, though, with those servers, that solution still is that it doesn't let the system be very interoperable. You have to go to one provider today to do all the signing because they control the keys on their servers to make this work. So this kind of seems like a backwards approach in some ways, but having thought about this, this is really still the only way to go, where we have to pre-compute all of the answers ahead of time. So the way you do this is saying, here's what I have, and what you want's not there. So it's kind of a long-winded expression of what's going on here. But the NSEC record is going to be used to say, here's the name before what you want, here's the next name in it, and then some other information. So for the example here, I have, let's say I added www.example.com, and I don't have that configured in the zone. There's no answer for that. But I have www and I have www.z are in the zone. So what you would come back and is you would get this answer where you have www.example.com with an NSEC record which says, here's the next name. So from www to www.z, there's nothing. And I want www, whatever. That would fit alphabetically between the two. It's not there. I can tell right away it's not going to be there. The other part of this, too, is that I list these types over here, which tells me what's actually at this name here. So if I ask for www.example.com and I want the TXT record, I want the text record there, I get back the same record. And in that case, I say, well, here's www.example.com telling me I only have a quad A and some DNSSEC records. So again, I infer from that there is no text record out there. So we had to create this thing, the NSEC record. Again, it's signed, and when I get this, if I get this back, if I had done the previous examples, and I cache just filled up with all of those keys and all those signatures and DS records or whatever, I get back this. It's signed by, the signature in here would say example.com and give me the key number, and I would just be able to verify that locally and say, okay, I trust that this is the NSEC record. It tells me here's what they have, but it's not there. Now, again, the odd part here is that this is pre-computed information. That's the big important thing here. And this is the way, and it's not just because of the top reasons where we don't want servers to be worried with this, but we also want to share this amongst operators out there. Now, there was a problem with NSEC. Now, can you imagine that before, when the DS started out, and I put data out there, and I can look up data and get answers back, one thing that still wasn't available was someone to actually just walk through the zone and see what's there. The NSEC record allowed people now have a way to walk through a zone. If you find a zone, like the root zone is NSEC signed. If you want to find what's in the root zone, ask for the NSEC records, and it'll tell you everything that's in the zone, and you can find all the information in there. There were a lot of people that were not happy with this, and so they said, we want you to go off and come up with a way that lets us say no without exposing everything we have, and with all the other problems we have out there. So what they came up with was a proposal, a approach which we create a hash of all the names. And so in this tree here, if you look at the zone here, you have, within a zone's apex, you have labels. And you may be used to zones which only have one level of labels out there, but you can have a whole tree inside of here. And NSEC would have a pointer across all of these names to show you what order they were in. But we don't want to show specifically what's in here in NSEC3. We want to have some way of making it a mystery. So we create a hash, a one-way hash, meaning that I take the data, I run it through an algorithm, and I get a number. Now, given that number, I can't go backwards. Hashes are one-way functions. I can only go from the data out. So I create a hash function, and if I were to take the hash of the apex, I have a value. And these numbers up here are totally fictional, but I have the hash up here saying the apex is a 1, the LBL1.apex is a 3, LBL2.apex is a 9, and so on down here. 6 and 2 and 6 are these ones up here. Now, these represent what's in the zone that's configured here. And notice these numbers are not in order. They're scattered. And in fact, in real life, if you look at these numbers, these are going to be really huge numbers. I'm using single digits here just to be clearer, but they would be very long, hex encoded, I believe, or base 64 encoded labels that would appear in your zone. They make things really ugly quickly in the DNS. Now, the other thing that's going to happen is when I want to query for this queue, and this queue is not going to exist in the zone, I need to know two things. I need to know that Q label 2 would be a 4 if it existed. I notice I have to be able to calculate that when I'm looking at the answer. This is where things get really hard to understand. And one other part of DNS is that if I look up a name and it doesn't exist, the DNS then uses a wildcard record. The wildcards record is there to say that if the name you really want doesn't exist, use this wildcard information to create or synthesize or just make up an answer based on this rule. So that in order to understand the DNSSEC3, I also have to know that the hash, the wildcard record down here would have its hash value of 8. I have to know this. These are not in the zone. That's why I believe they're italicized. It's hard to tell from my angle here. And so between these two slides, if I had like a wall-to-wall chalkboard up here, I could put this all up at one time, but I can't. It's PowerPoint. So I take this hashes, and I want to be able to answer that. I want to say no, that there's no Q, label A, label 2, apex. It's a query there. So I need to respond back with NSEC3 records. And none of them can say they have anything to do with any particular name. They have to hide their identities. So I have to go up here and I say, well, I had to find that, to show that 4 doesn't exist, that there's no hash of 4, because if the 4's hash existed, that meant Q is there, and that's not what I want. I want to show that the person asking that there's no Q. So if I say that hash number 3 to hash number 6 exists, meaning that 3 is there, 6 is there, but 4 and 5 are not, that means the name you asked for is just not there. That's pretty clear, though it's obfuscated by the hashes. The next thing, though, is I need to point out that there's no wildcard. And the problem is, how do you tell what is supposed to be a wildcard? So the first thing is, I need to show which is the last name I traverse, which last label I traverse before I found out there's no Q. And let me go back here and show you that if I'm doing this thing correctly, I go for apex is not Q, then I go down to label 2, because I want label 2, label A, and down to Q. Label A, this is a special name. It's actually got a term called closest encloser. That's the technical jargon term for that. I mean, that's the label where this Q would be sitting off of if it existed. It's also going to be the home of the wildcard by definition. So I have to, and this is all because I've taken this tree and flattened it, I need to tell the person about the structure of my zone. In 3 to 6 says there's no Q. 2 to 3 tells me where there is a 2. That means there is going to be a label A, label 2, apex. Now, the querier can find that out because they know what they're coming down. They say, well, I can figure which of these names is going to be a 2. All right, so I know that this is the name that existed. That was the end of the trail. But now, is there a wildcard? Well, the wildcard would have been star label A, label 2, apex, hash of 8. So I also have to throw in the NSEC3 record saying from 6 to 9, there's no 8. This is really weird. Does anybody understand this? Does it seem clear? All right, 1, you can leave. 2, you can leave. Sorry. This was built to be hiding information, and it does a really good job of it. The problem is that people have figured out how to break the hashes, and we won't get into the strength of the NSEC3 approach, but it's really hard to understand. It's really hard to get this out. And the weird thing is, the proof here is much different from the proof you would have expected, which is why most people can never really explain why this works. So there are very few people who actually can get this right, and people don't like it much, but it's very important for many reasons that it exists. So that kind of covers quickly how the validation process is working, the nuts and bolts of it. And I'll get into some of the other things around the fringe of this process. So what do you need in place to do validation? One is you need to have a name server configured to do the validation. That's getting simpler over the years. Configure, build, install with cryptographic support. I have to admit, these slides are about 3 years old, and the state of the art has advanced quickly in the last 3 years compared to even the previous 15. Proper trust anchor management is something which has become much more of something I've been aware of in the last 3 years with the KSK rollover. And then a time of day. Time of day is something that generally gets overlooked, but nowadays with some of the new devices out there, like the IoT devices people talk about, they don't necessarily know what time it is, but they need to do that in order to validate information. So I'm going to look at some of these in the reverse order I have up here. So time of day. Validation, we have those signature records with the dates in there, and the reason for that is, again, we don't want to replay information. We don't want to let someone say that this was true 3 years ago, believe me now, when it's been changed. I've seen examples where people have moved servers around. I've seen people change hosting providers. I've seen all this out there. The address record for a mail server may change significantly enough that you might see your mail going to the wrong place when they have signatures covering the old address. You don't want that. So we had to put time into the DNS, and it was a fairly new thing then, because DNS servers don't care about time when you think about it outside of the before DNSSEC. So at the time we designed this, we always assumed NTP, the network time protocol, was always going to be in place. But we're finding out that that's not always true, and also the NTP has its own security issues too. But we need to figure out, have these servers know what time it is relatively, so they can not replay the signatures. The next thing is trust anchors. Trust anchors are going to be the thing that you believe when you believe nothing else. If you have no trust anchor in there, you can't do DNSSEC validation, because you can go up this chain forever, and you're going to wind up at some point with a key at the top end of the hierarchy, which is not signed by anything, and if you can't trust it, you're going to go nowhere. In fact, for some of the implementations out there today, the way you kick off DNSSEC processing is just giving it a trust anchor, and then from then on it takes over. The trust anchors are very important because it's what you believe in. Now, you have to be kind of careful about that, because what you believe in is going to be up to what your policies are going to be for belief. So one thing I should point out too is that it's very tempting where we are with operations to believe that there's only the need for one trust anchor at the very top of the tree. DNSSEC was never built to be assuming the entire tree was signed. So we allow for trust anchors to be anywhere. You can trust anything you want. If you want to go out and get .com's KSK and consider it to be a trust anchor, you can go do that. The problem is they may change their key at some point, and if you don't know that, you're stuck. You may want to use a trust anchor for your local university, your local work unit, inside a firewall, whatever. There are times when you want to have that trust anchor, but you have to be careful that once you have a trust anchor, you manage the trust anchor knowledgeably. So you determine the way you trust it. Now, for the root zone KSK that we've been managing, we're talking about the last couple of years, we try to do a very large scale way of setting up the trust. But you have different ways to get this. You can get it any way you want, but verify what you have. Now, one of the things that's improved in the last couple of years is the tooling that is available to inspect these keys. Because these keys, the trust anchors, are configuration elements of your server. They're not part of the data stream. They're not going to be seen across the network. You can't query your server and ask it, what are your trust anchors? If you're running a DNS server and you have query response to go report 53, that's the way most people see your server. But you also probably have some other management hook into it. The one I'm most familiar with is Bind, and they have RNDC. I'm curious, how many people here are operating DNS servers now? How many are running Bind? How many are running Unbound? How many are running the not resolver or Power DNS resolver? Okay. Unfortunately, I'm not as familiar with the others as I should be at this point, but I can tell you that with Bind, it has a management control called RNDC, and RNDC is set up so that it's meant to be that the operator of the server can get in and ask questions of the server that other people can't ask. You can update the server, you can dynamically update the records in it, but there are ways now through RNDC and also in Unbound and the other tools have ways of asking the same similar question through the management interface. What are your trust anchors and what do you have there? Because they're configuration data, they're not available on the network, and you need to manage them carefully for that reason. It's very important that you have the current trust anchor out there. Otherwise, your DNSSEC is just not going to be, it's going to give you the wrong answers all the time. If it's no trust anchor, you're getting nothing, no protection at all. So now there are two ways that we've talked about managing trust anchors. We do manually. People can actually do their own trust anchors the way they want. They can, in fact, one of the issues we've had is some of the older configurations out there had manual controls for this stuff. When we've gone to automatic, we have this thing called automated updates of DNSSEC trust anchors, which lets people who are running zones that they know people are going to trust signal that they're changing their trust anchor. And we've a few examples of that out there. A couple of CCTLDs in Asia do this. ICANN has been doing it with the root zone the last couple of years. It's RFC 5011 is the IETF document number for this. And the idea is that you can as an operator and a resolver can set it up to say just automatically give me the right trust anchor, and it follows a certain protocol which is secure in updating itself. There's different protections against abuse in there, but you don't have to do it that way. Excuse me. You don't have to follow that, but you can. Depends on your level of tolerance for having your servers configure themselves. You may do that in a certain way where this is done on a canary machine, a machine in your NOC, which then tells you to manually update the other servers out there. But you have different ways of doing this. And the automatic way is easy, but the manual way is more like you really understand what's going on there. We do find, though, that with the manual server, one of the fine things we found in some experience is that sometimes we'll have an operator who's very energetic and decides they want to do DNSSEC, and they bring on validation, and they manually configure the keys, but then that operator gets promoted. They become manager somewhere. They hire someone else in who comes in and looks at this machine, doesn't know anything about DNS, has to learn on this, and they just don't understand this, and they find that the manual configuration is obscure. Years go by, and suddenly the machine stops working, and we've had a few people call and say, what happened? We have to explain to them that you had a server running and you didn't know about it. So that's why manual and automatic are things to look at here. So now I'm going to make a case for the root zone KSK. We hope that we try to encourage folks to configure the root zone's KSK as a trust anchor. There's a lot of information about that around. We do RFC 5011 automated update semantics for changing the key. We're in the process of doing that. And I'll have a talk on this later in the week about where we are with that project. But it doesn't have to be the only one. It doesn't have to be your only trust anchor. Where can you get the root zone KSK? You can get it's in the DNS. Of course, you're looking at the DNS. You're trying to protect yourself against bad answers. But if you're looking at the KSK, is actually right in there. You ask for the root zone's key set, and look for 257. You'll see that that's the key set we have in place. Now, I wouldn't necessarily just trust that right away, because if you're under attack or something's being hijacked, you might get the wrong answer, and that's a bad thing. There's also a website out there. There's a file that is under IANA.org, which has the DNSSEC files, and it has a XML formatted piece of data which has ways of verifying the key. And we've also worked with a lot of the software update, software vendors out there, software producers, that when you download a new copy of the DNS information, they're going to have that key hard configured already in the software out there. This is another way to test that. So why would you need more of them? Well, maybe you want to have other parts of trust. Now, there's also, in the world today, we have the root zone signed. About 90% plus of all the TLDs are signed. Not all of them, 10% are not signed. And you might, if you want to go to someone's organization and they're one of the unsigned TLDs, you may want to get a trust anchor for them. If it really matters to you to get trusted information from them, you might want to trust anchor that. And also, all the operators you have around, you may decide that you want to put other more specific trust anchors for what is signed, to make sure that you aren't going to be messed up by someone changing the zone above you. Depends on your level of paranoia. How afraid are you of the world? So now trust anchors have been around. They were one of the early concepts in this working, because you have to start somewhere. But in the last couple of years, we had a thing called negative trust anchors. These are trust anchors which you say, I don't trust that. Actually, turn it off. Ignore what you see there. And this comes from a story I'll have in the next slide. But sometimes, when it comes to operations, we decide that we want to turn off DNSSEC for all, ignore the fact it's out there. We want to say cut off all the stuff out there because of something that's gone wrong. This is actually another, it's called Definition and Use of DNSSEC Negative Trust Anchors, RFC 7646, which came out after an incident we call the case of NASA.gov. I forget now how many years ago this was, but there was a time in the U.S. when Comcast is still a dominant provider of services throughout the United States, and they had been running DNSSEC. They were one of the pioneers in DNSSEC validation for their customer base. They turned on DNSSEC, and they spent a lot of time and energy in making sure it worked right. They were on top of this. They weren't like someone who just turned it on as an experiment and then forgot about it. They spent a lot of time watching it and carefully managing it, and they had it going. They had their validation working. NASA.gov, under some U.S. mandates, had also signed its website information because they had to, and they try to do a good job. But I have to admit, I once worked for NASA.gov, and well, sometimes things don't go well. They launch good rockets, but everything else not always so good. So one day, NASA.gov did DNSSEC, and they kind of made a mistake. But on this day, there was a special thing going on in the U.S. Congress. There was a hearing related to Comcast and something about network neutrality and all this other stuff going on there. And the NASA.gov site became unavailable. Now, people who are fanatics of NASA.gov like to see space pictures, they like to see rocket launches, they like to see planets, they like to see data. They noticed that Comcast prevented their customers from going to see this government-provided information. They thought, this is an outrage. How can Comcast, being investigative or being fighting some rules of the government, decide just to say, you can't get to NASA sites until we get our way? A lot of outraged customers that day. A lot of venom, a lot of people were very mad, posted all over the place that Comcast was doing a bad job. The problem was that NASA made a DNSSEC error that day. They tried to change their KSK, their DS record. They didn't do it right. And because of that, all DNSSEC validation died. We learned a couple things that day. First, that Twitter is faster than an ISP's monitoring. This is the more humorous outcome of this. And this is being told by the NOC engineers, that they realized that even though, despite the fact they had a really good way of validating everything, they checked everything. They actually had really good operating scripts. But they had so much to cover that as they went through polling and finding this thing, they found the NASA.gov passed its thing. The badness happened before they got back to testing it. And in that cycle, people all over the place went to Twitter and said, Comcast is fighting the US government. Not a good thing to do. So speed of Twitter came out from that point when it comes to, actually I think it was Twitter was faster than Nagios was the term. But it also brought back up to this idea that we want to be able to ignore validation at times. Now, protocol purists at that time were like, how could you possibly do that? The DNSSEC is meant to work perfectly, and the protocol works. But in operations, things go bad. And quite frankly, in DNSSEC operations over the years, there have been more mistakes in operating DNSSEC than there have actually been attacks defended by DNSSEC. So we have to deal with the fact that operations of DNSSEC have not exactly been the easiest thing out there. This got negative trust anchors, which is an idea that had floated around, to become real. I wanted to have a way to turn it off for some time. And if you go from tool to tool, in fact, I actually do have information about that later. So I'll skip ahead to this. So how to set up validation. There's software, which is known. This is the list of software I had. And admittedly, this is the part of the slides that I spent a little bit less time preparing when I put this back together a few weeks ago. I've noticed that the dates, things have changed a bit. Bind unbound windows are out there. Secure not resolver, parallel DNS recursor have all become more active. Nominum Vantio is now part of Akamai, so I'm not sure what the name of that is today. DNS Mask is another piece of software out there which does validation. And Secure 64 DNS Cache also does something, although I'm not sure of the state of that product anymore. So Bind, the one that we all know and love. There's your plug. So ISC.org, Bind, current versions that are being updated, 9.11.5 and 9.12.3. I did look that up just recently, so that is up to date. You can download that, and it has the longest track record in DNSSEC. The guide to validation, this is the best guide I had up on top I could find. Over time, there's been different documentation. It's simple to configure. You can set up a Bind server and say, just DNSSEC validation auto, and it takes care of everything. This will take care of trust anchors. It'll do all the automated updates, and it will let data through that. It'll let through, and it'll stop data. Native trust anchors, an interface which I have yet to play with myself, but there is through RNDC, NTA for negative trust anchors, and you say what you want to have blocked, DNSSEC validation turned off for, not blocked. And the management of all that is taken care of automatically. I think you can probably change some of the parameters there, but it's a simple interface. NLNet Labs Unbound is another very popular recursive server on website unbound.net. It's a caching only name server. The Bind server does both authoritative and caching, authoritative and recursive. But Unbound does only the recursive side of this. And of course, Unbound is a play on the word bind. People seem to like to do that in our field. And it has tools for trust anchor management called Unbound Anchor. Before starting the server, you run to unbound anchor. This actually goes out and searches for the keys and validates them certain ways. It uses the IANA XML file, as we call it. It'll get that. It'll put that. It'll configure the keys. And then inside there, I say auto trust anchor file, and I have a file name where I put my keys, and it starts going. Now, for negative trust anchors unbound, I'm mentioning this because I find it a little interesting that this is different. Inside the configuration of it, as opposed to the side channel management, I say domain insecure the zone. I reload this. Now, that will always be there. It stays there all the time when I reboot the server. I can also go through their side channel management and make it insecure for a while. I have to add it and then remove it. The negative trust anchor and bind. It's automatically timed a certain way. In this case here, it's put in until you take it out, and so on. This is the difference between these two interfaces. I think is significant. Kind of gives you an idea of the level of maturity of the idea of negative trust anchors. It's a newer concept out there, a little bit controversial about what happens if someone turns it off and leaves it off forever. You know, they're just unprotected. But it's a new and I know I can say it's a very important feature to have. I tried to get it earlier, but it didn't happen. But we have to recognize that sometimes we make more mistakes in operations than we actually have attacks on the network. So other open source DNS, these two, Power DNS and Not Resolver, I owe them more time than I'm giving them here right now. And to fill in for that, I have these two URLs. And the reason why I left the URLs in there is they do a really good job on those pages of describing DNSSEC for those two packages out there. And I wouldn't do it justice to repeat or try to summarize what they have there. Power DNS is open source from folks in Holland, in Netherlands. And Not Resolver comes from the folks in the Czech Republic. They do the CCTLD there, and they have lots of different software available. Now, Microsoft, I have to. At one time, the slides I had here for Microsoft were really up to date, but now it's been 3 years later, so I may be a bit behind. I'm not sure if they have a server newer than 2012. I'm sure there are, but I'm not sure of that. And they have DNSSEC enabled. And in Microsoft's setup, if you add a trust anchor, DNSSEC is done. If you don't have a trust anchor, it's not done because it can't be done. They've been pretty good at trying to get DNSSEC out there. They have a tutorial, and they have another URL down below on the page that help you find information. They have, and I have to admit, I don't even have a license for Microsoft, so I haven't been able to try it myself. They have different interfaces to their system, and they recommended the PowerShell, and they all have the same settings available, but they have different instructions for how to turn on DNSSEC validation. So enabling it, it's the default session, just you set it on, and you add trust anchors because they have to be there, and that's the kicker. And you can add lots of other ones out there. There's a website that describes how other trust anchors are in there. Other trust anchors may be important if you're running an inside-outside DNS called split horizon sometimes, or split DNS. If you're running a different DNS inside your organization, you may want to have a different trust anchor for what you have internally. And I had this situation years ago where I actually want DNSSEC to be stopped for my inside the organization zones. That have been a negative trust anchor. So managing these servers on there, standalone servers, they have a trustanchor.dns file, and they have different ways to, they have different tools ready for their viewing trust anchors. The bottom is very important. So actually got through this in an hour. I thought it was going to take me hours to do this. DNSSEC validation is a good way to protect the interests, because if you don't do validation, you don't know the answers that are coming into you are going to be secure. Anyone can forge them. And recently, there's been a lot of attacks out there, and I still need to go through some of the understand all the attacks out there, but there are people who are able to send bad responses to DNS because they hijack the routes of the servers. So you actually go to somebody else's server out there. So even if you have a server out there on an address, and you know that you've got the server well protected, and people ask questions to there and get answers from you, if someone were to change the routing table so that the queries would never get to your server, you know, unless you're monitoring traffic levels and they drop to 0, you wouldn't know you're being hijacked, and your answer is going up somewhere else. Now, the thing about this, the private key is, if the private key really is kept somewhere really secure and private, whoever's hijacking the route and sending it to another server can't change your answers on you, right? they don't have a way to generate the signatures that are going to work here unless they mess the tree up higher. So that if someone's validating, will see right away, hey, this is from a hijacked server. Nothing is validating. I won't accept it. And if they say, well, I'll just do a negative trust anchor, they better check to make sure there's a reason for the negative trust anchor. They may want to call up someone and say, is this really something I should block at this point? So DNSSEC can actually help detect when the wrong server is answering you because of a route hijack. Of course, all this is dependent upon the information above the tree also being, the DS records basically being intact. So this is something where DNSSEC validation is probably overlooked. One of the things I like to equate this with are seat belts in cars and automobiles. When you travel somewhere, seat belts will help you, could save your life in an accident, but we don't normally have accidents, so you don't normally know that. And seat belts can be a pain in the neck because you can't get them unbuckled or buckle them at times. So it's kind of the same thing. It's a protection when really bad things happen. Bad things happen rarely, but it saves you. And normally you don't need it, and it's a pain in the neck. That's how validation is. The best we can do is make the tools available to help manage DNSSEC validation, make it clear what's happening, and when things are going wrong, help you debug what goes out there. So with that, I hope this gives you an idea of what validation is about. And if you have questions, any things you want to bring up, raise your hand, come talk to me. And with that, I'll give you an extra half-hour break. Right. Oh, and the obligatory I work for ICANN slide. So.
Could you tell me the page 99 that is show the process of the validating the keys? Before.
This one?
No. No. Ah, yes.
This?
Yes.
Okay, so let me go back to this slide here. So this is the query to get the root zone's keys. Mm-hmm. And the reason why I did this query is because I see the DS record for downward signed by the key that's in green. Mm-hmm. Right. So I get back this over the network, and I have the key is in green. That's the data I want. That's the key I need. Because with that key, I can then do the validation process where I have the data, which is the DS record, the signature, that's the DS record signature, and then I have this key. Mm-hmm. So the next question is going to be, at this point here, how do I verify this signature here, right? Mm-hmm. So, and that's verifying this signature here over this set, right? Now this is signed by 20326, it says, and here is 20326. Now here's the issue that comes up here. This key 20326, I can have configured in my trust anchor database, my configuration file, right? But I'm being told over the network, here is 20326. What if this 20326 in here is a forgery? What if that's incorrect, right? What if it just says that that's 20326, right? Well, if I use that to verify this, I'm not really trusting what I want to trust. So I want to make sure that that key really is the trust anchor key. And that's the detail I kind of don't have clearly enough at this point here. From this point here. But there are different ways to do this. That when an implementation sees this key over the network, it can then compare it to what it has, right? It's important that they compare it to what it has, right? If they're the same key, it's good. It could also be that they ignore the key that they learned over the network and use only the key they have hard configured, which is better. But in a little bit of detail here beyond what the slides are, some implementations have essentially the DS record for the root zone. Now, DS record for the root zone doesn't exist. It's just a made-up configuration parameter, right? In that case, then I would have to use that information to point to that key I've learned online. That last link is actually kind of important Now, it comes from the fact that what are the chances that this key, what are the chances this key is the incorrect key? And there are a couple of reasons why it's hard to do that. For one thing, that 20326 is not a number you see, it's calculated. But it's only 16 bits long, right? And the keys are really long. So it's possible to have many keys have the same key tag. So there are different things that can happen out there. It's possible to have two keys with the same key tag. But you just want to make sure that at this point, and this is a question for the implementers really, is to make sure that they process this last query and understand that the key that they're learning over the network isn't necessarily going to be the same as the one that they have trusted up here.
Okay, thank you very much.
Sure. Okay. Yeah. How long is it? Sorry? Well, I'll give. Yeah. Yeah. Let me say. Yeah. Yeah. So as far as the KSK key rollover, outside of a plan to do it again, there right now is no timetable. Right. That doesn't mean it's not going to be done. What's happening now is there will be a couple of meetings coming up that I won't be at. Meeting in the ICANN meeting in a few weeks. Kobe meeting. I'm sorry, I don't even know when that meeting is. ICANN has a meeting coming up in a few weeks, and there's an IETF meeting coming up, and I believe one other meeting where they're going to have ICANN will have sessions, asking people to say, what do you think we should do for the next time around, right? And that's just to find out what do we want to do next. Now, in terms, we have yet to make any determination about a regular schedule of a key rollover, which is your question basically is when will the next one be? The answer is it's not scheduled yet. That's a simple answer out there. But we'll be looking for input for this, and we're working on what will happen. There will be more. There will be more. We just don't have any agreement on the frequency or the timing for that right now. Okay. Sure. So let me say, so actually your first question was about the timing of the next one. That was for those who might be hearing us only remotely. So this question, let me see if I understand your question. I may not have the. So when you're doing the rollover for our end of the rollover, okay, so on our end we have a set of authoritative servers for the root zone, root server operators, right? There's A through M of them right there. And they're all pretty much the same. There's nothing different between they're different operators, but they're all kind of on the same level of the hierarchy. So when we do the rollover on our end, we change all of them at the same time. And so you'll see that the same across. Now, for anyone else out there who's serving authoritative data in DNS, they shouldn't have any worry about this, right? The only thing that came up in the entire rollover where we asked, at the time we were making the critical changes, we tried to suppress other major changes from the TLDs coming up, just to keep the process smooth. But if you're running anything else, if you're a registrant, if you're a commercial registration or anywhere out there, the keys that we're rolling over the KSK should have no impact on your signing process at all. Right? Now, if you're doing the validation, that's where you have to make sure that your trust anchor database, that the configuration database in your recursive server has the new key. And certainly, right now, if it doesn't have the new key today, it's not working at all. Right? If you only had the new key a year ago, it wouldn't work either. So it was only during the rollover it gets very touchy to make sure you have the right key. And the two things, the most important two things, this was that in the DNSSEC world, there's no way to know who has the key to make sure you know about it. We couldn't say to everybody, "Do you have the key?" Update. But the other part of this is that, okay, I'm sorry, I've kind of lost my train. There's no way to test it ahead of time. We were kind of stuck. We just had to roll the key and see who had trouble and see them fix it. Right now, making a lot of conclusions about this is a little premature, actually, because we're still not quite done with the rollover. And I would talk later in the week about this, which will show some data. Yeah, as I put the talk together, I realized that we're still learning about this current rollover to see what's going to happen in the next month or so, and so on. So, did that cover your question? Okay. All right. And I have so I have a question in the back. You way in the far back. I think I'll repeat the question. Okay. Okay, so I'll try to summarize what Jeff said here for the remote whatever. So the different understanding of the question was that whether or not the difference between rolling the key at the root zone versus rolling the key lower in the tree. And yes, rolling the keys regularly is good practice, as Jeff was saying. And for those in the room, I'm just repeating what Jeff had just said. It's good to be able to do something in an emergency that you've rehearsed when it's not an emergency. Always good operational tenets out there. You want to make sure you can do everything in operations when you need to do it. Now, doing that for yourself when you're lower in the hierarchy than the root zone, it should be not a problem because you have the hierarchy above you to help push to help roll your keys with that. The root zone is special, as Jeff said. The problem here is that there's no one above us to help us push the key out there. And it's actually, and if you look at the workload, what happens out here, and I have, again, this is a whole different set of slides I have later in the week. Changing the private key is easy for us because we do it in one place. The change of the public key has to be done by each and every person throughout the internet that's doing validation, right? If you sum total all of that, that's a lot of work, but each doing the same small thing. Coordinating all that is very difficult. And if you're on the edge of these, if you're one of the people that is running DNSSEC validation and we're not aware of it, and there are quite a few that were in that bucket, you're really kind of out in left field. You're really kind of out there because you didn't know you had to make an update and you need to make an update. And yes, disruption is bad, but hopefully it's a small amount of pain that gives us a huge gain in terms of readiness at the root zone and make a change in emergencies. 1, 2, the next time it happens, you'll know about it. And 3, hopefully we would like to learn how to make this even more automatic, right? And that's going to be some of the considerations I have coming up in the week. So yeah, it's an inconvenience to many people. It's a minor outage for some. It's a major outage in smaller areas, But we have to get past it. One of the problems I had with this whole process is that if we could not handle changing this key, the internet is really in trouble. We've got to make sure that we are adaptable all through the tree, all through the internet, when things like this will have to change, because there'll be bigger things coming down the line at some point, especially when you go to if you want to go for a network which is built as it is today to one which is very secure and reliable. The way you become secure is you start constraining what folks can do, and we have to get used to that. So that's a whole philosophical talk for another place, but hopefully now we've given you what you're really seeking. Yeah, thanks, Jeff. All right. So we can go back to email or to the break, I guess. So. Sure. No, well, in this case, we hash a very small piece of information. So, let me show you. I think that they're already uploaded. Sorry, I'm just.
No, that's fine. I just check it.
Yeah, I think that the slides should all be available through the Apricot website, although I don't know how yet. I looked. The reason why is I actually looked for that earlier before.
No, that's fine. Anyway, I'll send you an email on that.
Okay, sure. So if I do, oops, oh, no, my network turned on. 'Cause normally caching is, let's use, caching, or hashing, you think of like you take a textbook, a book, and you take all the words and you hash it and you come up with a small, right. In this case, you have the same process, but the